next edition of Physics 100. Now, if you're taking a non-algebra based class, this would be the start of your second semester. So the last lecture would basically be the end of your first semester, more than likely. And this is the start of the second semester, which starts with electromagnetism. In the trig and calculus-based versions of the class, for the second semester, this chapter actually represents the most difficult chapter of the entire semester. And they give it to you first. In this class, since we don't do sines and cosines, and we tend to do things in one dimension, this one's not quite as bad, although this will be one of the tougher chapters for the second half of the course. Not because it's too dreadfully hard, but because we're going to have a lot of chapters with a lot of concepts. The math equations are going to be a lot more straightforward, basically like the last lecture you saw on sound. You can see over here there are a bit more equations for this particular chapter than for the last one, and some concepts to go in there as well, and some symbols and constants to keep track of. And I'm on the second slide, not the first one. So our goal for today is to begin to understand electrostatics, which is just individual charges that usually are stationary but they can move as well. Objectives, we're going to understand what charges are, we're going to learn how to produce a charge, and then we're examine the tricky part of it, calculate electric field, electric potential, electric force, and then we'll do a few other random items. So what is charge? Well, there are two parts to an atom, so we have to understand the atom before we can understand the charge. Or you just use your credit card, that's charge. Just kidding. So there's the electrons and the nucleus. The electrons have negative charge, the nucleus has positive charge, and usually they have equal amounts of charge. So there's one electron for every proton, they have equal amounts of charge, so the net of charge is 0. But if you find a way to separate the electrons from the nucleus, then you have charged particles. So ways of charging things are ways of removing electrons from that atom. Charge is measured in units of coulombs, which abbreviate as C. The symbol for charge is Q, which makes no sense in English, but if you use Italian, then it makes perfect sense. And usually there's two different charges that you care about in a specific problem. There's the charge that is creating the field or creating the force. I call that charge by. And then there's the charge that is the force is being exerted on, and I call that charge on. So that's sort of my new nomenclature. It changes a little bit from what you'll see, say, in the textbooks. So I do things a slight bit differently because it's my hope that this will make more sense. If the book makes more sense, you can understand how it's all set up, then by all means use that. If you're not in my class, there is a sign, well, I don't want to say sign error, there's a sign discrepancy with this particular equation here because I use the opposite direction in the equation than the equation that's assumed in the textbooks. Oftentimes they'll assume directions and not tell you that they've assumed a direction, and that can mess things up because directions are very important, especially for electrostatics. Direction is insanely important, and if you leave off direction, you will be absolutely lost, especially if you're in a trig-based course. But since this is the algebra-based course, directions are a little bit less important. Still important, but not so much so that they're going to completely destroy you. Now, there's something called an elementary charge that's a constant. It is 1.6 times 10 to the minus 19 coulombs. The elementary charge represents the charge of a proton if it's positive. And if you put a minus sign in front of that would be the charge of the electron. So one electron has a charge of minus 1.6 times 10 to the minus 19, and one proton has a charge of plus 1.6 times 10 to the minus 19. And those are called elementary charges. Oftentimes on equation sheets, you'll be given the elementary charge, and you'll be expected to know that the protons are positive of that, and the electrons are the negative of that. And the elementary charge is abbreviated with a little e. Like that. And you'll be expected to know that that's the elementary charge. Like charges repel. So if you have two positive charges or two negative charges, they repel each other. Opposite charges attract, so a positive and a negative will attract each other. And charges can actually move around. Otherwise, it would be a very boring universe. So how do you get charge? How do you charge things up? Well, there's a few ways that you can do that as a human being. And there's one that really don't do it quite as often. You can superheat it, which is not on this list of three. And that creates something called a plasma, which is all charged particles. But doing things safely at room temperature, you can do it by rubbing. Like if you rub a balloon on your shirt, what happens is electrons get ripped off of atoms between the balloon and the shirt, and so one becomes negatively charged, the other becomes positively charged, and then fun things happen. Induction, if you have a changing magnetic field, this can create a charge, sort of, because it'll move charges, and so that you can funnel those charges somewhere, and that'll allow you to create a charge. And it turns out this is how almost all the electricity in the United States is produced, is through induction. More on that in a later chapter. And conduction, you move charge along the wire, so you move the negatives over here, you're left with positives over there, and so you have two sets of charges. All right, so that's the basics. Hopefully everyone's up to speed. Now for the measurements, because in science we don't generally care how the charge was created. We care about what its effects on everything else are. Especially in the modern day where we have electronics and electricity everywhere, these are very important. So suppose I was looking at water on a rainy day. And it rains everywhere. And I want to know where all that water is going to flow. For whatever reason. I want to build a better sewer system. How would I measure that? Well, I would use a field. The field would tell me where the water is going to go. In this case, I use a gravitational field. And water goes from high gravitational field to low gravitational field. In other words, it goes from high elevation to low elevation. From high gravitational potential to low gravitational potential. Now, if water had negative mass, it would do the exact opposite. So, fields are listing the possible potential for some given object at some given point. And the gravitational field is measured by topography. Now, I'm waving my hand a little bit there, a little bit here. So water will want to flow downwards. Charges would do the same thing. They want to flow down the electric field. Unless they're negative, and then they want to flow up the electric field. And so it gives us a way of being able to measure the electric topography of the region, if you will. And as a result, protons or positive charges are hills. They're higher, electrically speaking. Negative charges or electrons are sinkholes or pits. They're lower, electronically speaking. And positive charges will want to move from the top of the hill to the bottom of the valley. Negative charges will want to do the opposite. They want to mountain climb. So people who climb Mount Everest, they're not crazy. They're just think they have negative mass. They're negatively charged gravitational particles. Okay, not a good way to look at it. And the elevation is measured by the electric field. Now the electric field is in units of newtons per coulomb, and has direction. Now the direction that the electric field points is the direction that a positive charge would move if you put the positive charge in that electric field. And so that's why direction is very important. The negative charges would move the opposite direction to the direction of the electric field. So calculating the electric field for just one charge is pretty straightforward. The electric field equals a minus, actually let's see here, I gotta make sure I have this correct, because the textbooks put that minus in. I did not. If I have a positive charge that wants to go away from the protons, it's going to have a minus, yes. Sometimes even I have to reason it out. As I tell you students oftentimes, when in doubt, reason it out. This is probably the first time you've heard this on my video, because I actually came up with that saying after I did the first videos. And I know I've annoyed you with it to no end at this point in the semester, but I think it is a good statement because even I have to reason it out. So, minus k, so I'll just use this one, it's a little bit better. Minus k is a constant. It is equal to 9 times 10 to the 9th in physics units. And here are your physics units. Sorry. So it's just a constant. Times charge by, I know I didn't put that on the slide, but it's charge by. That's the charge that the field is created by. So I have a charge that's sitting out here, that's creating an electric field everywhere around it, and this is charge by. By the way, charges do not create fields for themselves, so if I wanted to know what the field was at the location of charge by, I would use every charge in the universe except for charge by. Because every other charge would then be charged by, and it would be charge on. So if you're measuring something at a location and there's a charge at that location, that charge will always be charge on. All other charges are charged by, because they're the charges that the field is being created by and the force is being created by. Here I only have one charge, so that charge is automatically Q by. Divided by the distance squared, that's what this R means. The R is the distance between where you're measuring. Let's say I'm measuring from here and the charge. This would be R. And I would square that, or my distance, and that would be what I put here. Now the direction. Direction is very important. The default direction, and you always use this, is towards charge by. So it's all, in this case, it's going to be, my direction would point that way. If I set it up, I was measuring it from here, my direction would be in the plus x direction. I think I've used this notation for you before. And if you're not in my class, you've definitely seen this notation before. And if you're over here, it would point in this direction, so the direction would be minus x hat. And that's what we would put in this parentheses here. Now, if you have a minus sign, like so, that minus sign can then be used to cancel out that minus sign. And then if you had a positive charge, if you were looking right here, the electric field would point that way, which is what you expect, because if this is a positive charge, the field should point away because the positive charge would move away from the other positive charge. So that's a way to do what we call a sanity check to make sure you did everything correct. If you do it this way, you will always get the right answer. If you try to guess the direction at the end, well, you could kind of do that, but it's a little bit more difficult. I don't recommend it. All right. But how do we translate this to a force? Now, the equivalent of now there's equivalence between the gravitational world and the electric world. In the gravitational world, you have mass. In the electric world, we have charge. In the gravitational world, you have, I'm going to call it little g. That's where the kind of the acceleration points. And in the electric world, you have E. Probably should put that backwards. I'm going to confuse you. Sorry, let's do that back. G and E. Now, the gravitational force is mg. And so, and points towards M. Or sorry, no, points towards the Earth, points towards the object doing the attracting. So it's towards M by, and this is M on. I know that's kind of confusing, but I'm using the same nomenclature I use with electric field and electric force. So the force of an object, if you have the electric field, is equal to the charge on times E. So if I have a charge here, let's call it charge on. This is the charge my force is going to be applied on. It's going to be pulled in some direction. And that force is going to be equal to the electric field times this. And since the electric field is going to have some direction, I'll just point in a random direction, the force is going to point in that same direction unless my charge is negative, in which case it would point in the other direction. And I don't have to have anything in parentheses here because E has a field, the electric field has a, so the electric field has a direction. By the way, don't confuse E with F. E is electric field, F is electric force. I know a lot of times we physics teachers can tell if you really understood the material because we'll ask you to calculate an electric field and you'll go F equals and solve for F, thinking that that's the field because field starts with F. And you've just declared in very loud terms that you were trying to guess. So, so make sure you understand the difference between force and field. Force and field. They both start with F, so it's a little confusing. But this is the electric field. So don't think of it as field, think of it as electric field. Okay. Then you'll be okay. So, so force equals charge on times E. Now, please note that charge by goes into E. So that means you're going to have both charge on and charge by eventually. So if you actually combine these two equations, you can actually get another equation which says that the force equals charge on times charge by times K divided by R squared, and I think there needs to be a minus sign in front of this, towards charge by. Yes, there needs to be a minus sign. Okay. So if these are both positive, this points toward charge by, but like charges repel, so that means they're going to go opposite direction. So if I have two charges, charge by and charge on, then the force on this charge equals minus charge by, the charge that's creating the force, times charge on, the charge the force is being applied on, divided by their distance squared, which is this, times the constant k, which is just a constant, and then the direction is toward Q by. And of course, if we're doing that in some sort of definitive direction, say left or right, up or down, and it's opposite the direction you're trying to point, like minus x instead of plus x, then you can switch that here with the minus sign to make it away from Q by. But please note, this is one thing I see people do a lot. Charges do not have forces towards themselves. So make sure you're using the correct charge. So sometimes I'll have charge 1 and charge 2. So Q1 and Q2. And I'll ask, what's the force on Q2? And they'll put some number towards Q2. So it's pulling itself, it's crushing itself, it's pulling itself in. So it's towards Q1. This one gets pulled towards Q1, and Q1 gets pulled towards Q2. And note, if you reverse which one's Q on and Q by, the only thing that changes is that direction there. So they point. So the forces are equal but opposite. Equal and opposite. Where have we heard that before? Probably that was a month ago, 2 months ago. I don't remember. Equal and opposite force. Anytime you have a force, there's an equal and opposite force. That's Newton's third law. Okay, so, and this basically goes right into that. All right, so Newton's third law aside, so that's the equation for forces. Again, this is for me. I'll give you a second to read it. So force equals Q on times E, where E has a direction, or it has Q on times Q by with a minus sign times K divided by R squared. And this one very much looks like the gravitational one, where it equals G M1 M2, where G is K, divided by R squared, and sorry, M on, let's use the same, M by. So if I'm being pulled to the center of Earth, I'm M on, Earth is M by, and it's towards M by. So the only difference between the two is we use mass instead of charge, G instead of K, and there's no minus sign in front. In part because there's always positive masses. And it's an attractive force, and this is a repulsive force for equal charges. Now, this leads us to a question. If the equations look similar, which one is more powerful? Electric force or gravitational force? So to give you a reminder, K, which I've written over here, 9 times 10 to the 9th in physics units. G is 6.7, not 6.67, times 10 to the minus 11th in physics units. All right, so which one is the stronger force? Gravity, electric, or are they equal? I'll pause for a moment for you to think about this and debate and probably change your mind 10 times. Okay, you changed your mind 11 times. Maybe I should give you the answer. All right, so if you pick that they're equal, that is incorrect. Okay, so eliminate that one. So it's either gravity or electric. All right. If you were in the classroom at this point, I'd ask you how many people with gravity, how many people with electric, and then I would say, well, you are both correct and incorrect. Because it depends upon the situation. Now, K is definitely more powerful than G, so that might lead you to believe that the electric force is much stronger. And if you have a charged object, then the electric force is definitely more powerful than gravity. Now this is very important because the only reason I am standing on top of the floor, the ground, and not sinking into the earth is because the atoms on the bottom of my shoe and the atoms on the top of the floor are repelling each other. That's an electric force. And is canceling the gravity force. So in this case, they're equal. Oops, I guess I shouldn't have called out the equal so quickly. But only in that situation. If I have two charged forces, the electric can actually be stronger than the gravity. This creates something called a maglev trend, where, well, that's magnetic force, but electromagnetic forces can actually counteract gravity and push you up, levitate you, if you will. And as you get further away, of course, then the force drops, and in which case the electric force would drop pretty quickly because R would change as a percentage very quickly. The R for gravity would change very slowly because your R is extremely large, and it's right now about 4,000 miles. 4,000 miles plus a couple inches doesn't really change much, but if your R was a couple inches to start with, and you change it by a couple inches, that's a pretty big change. However, I want you to think about this. What is your charge? How much charge do you currently have? Now, don't get out a physics book. You don't need it. Because we're looking at net charge here. Not calculating how much electrons and protons you have. You don't need to do that. How much net charge do you have? The answer is 0. Usually we are charge neutral. Most objects in the universe are charge neutral. And if I take Q on and make it 0, the force is 0. So in the universe, unless you have an object that's charged, gravity wins over electric. Electric only wins when you have charges. So electric only wins at very small distances where you see where the distance between the electron and proton is enough that at that distance you can separate, they appear to separate them out. But when they're very, very close together, and I'm at a large distance, then it doesn't matter, and I just see 0. It's only when I'm very close to the size of an atom that I actually see the minus charge here, the positive charge there, and I'm pulled towards one and pushed away from the other. And that's only then is that when it matters. And that's why we get things such as the strong force and the weak force, which happens on the cores of atoms to be able to hold them together. Even though you have all the positive charges in the proton, you would think that would repel, and you couldn't have a nucleus of an atom that was all positive because it would repel itself, but because protons have a positive and negative charge to the quarks, neutrons have positive and negative charges to the quarks, those charges together can create a field that holds them together, but only at very, very small distances. So gravity wins at big distances, electric force wins at tiny, tiny distances, or when you have a charged particle. Or a charged balloon, because then it can levitate up. All right, now we're going to talk about energy. Because if we have charges, they have energy, those energies are going to determine whether they are bound or whether they're going to escape from each other. They also determine how much energy you can liberate if they escape, or how much energy it will take to break them apart. And if any of you have taken a chemistry class, this all goes into all of chemistry. This basically is chemistry in a nutshell. So electric potential energy is very similar to gravitational potential energy. We abbreviate it with the letter U. All potentials are usually abbreviated with the letter U, which seems strange as heck, but that's the way it is. So the potential energy equals, there's no minus sign because the minus sign magically goes away due to mathematics that we can't cover in this class. If you're in 152, you know what mathematics is. Equals to K, my constant again, times Q on times Q by, divided by R. Not R squared, but R. Why is it R? Because when we learned about work was force times distance, so energy is force times distance. We take the force, which is Q on Q by over R squared, times a distance, R, and you get energy. And again, the minus sign went away because of mathematics. We don't cover this class. Now, please note that if charge on and charge by are both positive, the potential energy is always positive. So they will separate automatically, and you'll be able to gain energy out of that. If they are opposite charges, then the potential energy is negative. Now, potential energies are always defined to be 0 at a distance of infinity. So that means that if you have positive potential, that means the object will go to infinity and have some energy left over, which will be converted to kinetic. So you'll have whatever that will be converted to kinetic. You'll have that much kinetic at infinity. If you have a negative potential, it would require that much energy to get you to infinity. Now this leads to something I've kind of hinted at. Will an object escape or not? Well, if I take a ball and throw it in the air, and I do the gravitational equivalent of this, instead of doing mgh, I do the gravitational equivalent of this, which would be minus gmm over r. I'm waving my hand a little bit here, but only a little bit. And I add my kinetic energy to that, and ask, will this object escape? It turns out it's actually a straightforward problem. If the total energy is 0, my object will get to infinity and stop. If my total energy is negative, then it is bound. And it will get to a certain distance, its kinetic energy will go to 0, but it'll still have some negative potential. The negative potential would equal my total energy, and it'll come back. Same thing can happen with charges. If my total energy is positive, it escapes. If my total energy is negative, it will not escape. It will stop and come back. If total energy is positive, the kinetic energy will have will be equal to total energy, because potential energy will be equal to 0. Total energy is potential plus kinetic. This is something we looked at in the energy lecture. And so there's a very huge similarity between how energy is done for charges and how energy is done for gravitational objects. Kinetic energy is the same, it's just that instead of doing gravitational potential and converting back and forth between gravitational potential and kinetic, we're now converting back and forth with electric potential and kinetic. By the way, fun fact, a 1 coulomb charge is an insanely large charge. Usually charges are in terms of nano coulombs. So if you get a force or energy from a charge, I give you 3 coulomb charge, and it looks like it's obnoxiously large, it's because it is, because the charge is obnoxiously large. So, all right, now for energy, notice I did not put any direction like I did for the field and force. Sorry, field and force. Why did I not emphasize direction for energy? Well, that's because energy doesn't have direction. Energy is a scalar. It does not have direction. So no worries about direction for that. You just take the scalar distance, which is why I guess I put a big R instead of a little r. Although if you square the distance, the direction doesn't matter because you're multiplying the distance times the distance. Or direction times direction. A direction times a direction equals 1. A direction times the opposite of the direction is minus 1. A direction times the perpendicular of the direction is 0. There's some more fancy math that does that, but in this class, that's all you need to know. All right, so let's do some practical applications of some of the stuff that we use in real life. One is called an insulator. Think of like insulation for a house. The insulation for a house prevents heat energy from escaping from the house by absorbing or reflecting that heat and then sending it back. Wood is a good insulator for charges. So insulators for charges are things that you can put around, say, a wire that will keep the charge on the wire and from escaping from the wire. So wood is a good insulator. But we don't tend to use that because wood is also flammable and wires tend to heat up. So we usually use plastic, fire-resistant plastic. So insulators allow you to not be electrocuted every time you touch a wire. Conductors are materials that allow charges to flow, like metal. Copper is a really good conductor. Silver and gold are even better, but they're very expensive. Copper is about 15 cents an ounce. Silver is $15 an ounce, well, $14 an ounce as of making this. If you're watching this in 2025, silver is $4 to $5 an ounce. I don't know exactly where because I don't have a crystal ball, but pretty much super stuff. And gold right now is same. So conductors and insulators. Conductors allow you to move charge freely. Insulators allow you to stop the charge. But usually in science, it's not A or B, there's a spectrum of objects. And so there should be things in between that can act as either a conductor or an insulator depending upon the situation. We actually have those, they're called semiconductors, which depending on the voltage, which I haven't covered, we'll cover that in the next lecture, can determine whether the object acts as a conductor or whether it acts as an insulator. And this allows you to create a circuit that can do different things based on whether you change the voltage. This allows you to do computing. And it's revolutionized electronics because it allows you to make things a lot smaller. It's semiconductors that allowed us to take computers from being the size of, well, a giant warehouse and putting them in your watch. Oh, sorry, if you're from 2014, and you have a time machine that only sends you forward in time, and somehow you were able to see this anyways, but it makes no sense. And, you wouldn't have heard of the iWatch, Apple made a watch. I think that was the reaction of the world. But this revolutionized the electronics industry and continues to revolutionize it. But you can also push it further down the line.